is about this module is about on-farm drainage, and in this module we will be talking about the drainage at the farm level, at the tertiary level, and first we will talk about the need for drainage improvement. Uh, as you know that the drainage is removal of excess water uh, from an area. If you're talking about agriculture drainage, it is the removal of excess water from the root zone in order to create healthier environment for plant growth. And the although the irrigation uh, has already increased the agriculture production, but recharge brought about by seepage losses from irrigation network and deep percolation from farm irrigation has resulted in the rise of water table. So, due to poor drainage system at the farm level, we are facing waterlogging and salinity problem in many areas of Pakistan, and due due to this, lot of agricultural land has gone out of production, and drainage is one of the activity which help you maintain favorable moisture condition for optimal crop growth and to control salinity and waterlogging. So for all, in order to address all these problems, we need to have a good drainage system. There are many multiple functions of drainage. Drainage is used for waterlogging control, salinity control, erosion control, flood control, for the protection of environment, public health and rural sanitation, and protection of infrastructure, rural development, and food security. Uh, in this module, we will be mainly focusing on drainage problem related to agriculture. Okay, as uh, the curriculum which we are going to develop is integrated water resources management, which is basically a process that promotes the coordinated development and management of water, land, and related resources to maximize economic and social welfare in an equitable manner without compromising the sustainability of ecosystem. Drainage is one of the important component of integrated water resources management, and it not only helps in waterlogging and salinity control, but also uh, in the management of the system as a whole. Design may need to be modified to be able to exercise more control over drainage process and to avoid undesirable uh, drawdown of water table. Okay, and now we will talk about some of the important drainage properties of soil. The first and the foremost is soil water potential and soil water movement. Potential is basically the energy required to move a unit quantity of water from a reference state to the point of our interest. And in drainage studies, uh, two there are many components of water potential, but in drainage studies, two components are important. One is gravitational potential, and the second one is pressure potential. Gravitational potential is basically the energy expended or gained in moving water against or with the gravity force. And the pressure potential is energy expended or gained in moving water against or with pressure difference. So movement of water within the soil is mainly governed by these two forces, gravitational force and potential uh, pressure force. And soil water potential is basically sum of these two forces. And Darcy was a French scientist. He was basically a civil engineer, and he was trying to study the flow of water through porous media. And during his study, he developed, he came up with a law which is commonly known as Darcy's law. The Darcy law states that the rate of water movement through the soil is proportional to gradient of the soil water potential. And this is here you see the basic equation of Darcy's law, which basically relates the flow through porous media with the hydraulic gradient and area of the flow. And the basic equation of Darcy's law is basically Q is equal to KIA. K is the constant of proportionality in Darcy's equation, and this constant of proportionality has been named as hydraulic conductivity, which is one of the important property of soil, and this is used in the design of drainage system. And hydraulic gradient is basically the change in head per unit length. If you have 2 points A and B, and you want to determine the hydraulic gradient, you take the difference between the head at both the point and divide it by the distance between the points. By this way you get the hydraulic gradient. Okay, as we talked about hydraulic conductivity, which is the constant of proportionality in Darcy's equation, and this basically depends on the type of the soil, and different soil textures have different value of hydraulic conductivity. The table here shows you the hydraulic conductivity of different soil material. More porous the soil is, higher is going to be the value of hydraulic conductivity. As you see from this table, that clay or dense clay or clay loam soil has very low value of hydraulic conductivity, and sandy soil and gravel, they have very high value of hydraulic conductivity. Okay, other important properties of soil which are useful or applicable in drainage studies are field capacity, permanent wilting point, and available water. Field capacity is basically a property of the soil, and the soil is said to be at field capacity when, after a good watering of the soil, the deep percolation flow has practically ceased, and no significant evapotranspiration of soil moisture has occurred. And this normally happens 2 to 3 days after irrigation or heavy rainfall. Most of the soil reach their field capacity. The second term is permanent wilting point. Permanent wilting point is basically the moisture content at which the plant permanently wilts and fail to recover even if you place it in water saturated environment. There is a problem with the slide here. Definition of field capacity has been copied on the permanent wilting point. That need to be corrected. Okay, field capacity of most of the soil can be best approximated at by applying pressure of 1/3 bar on the soil, and the moisture that remains in the soil at that particular pressure reflects the field capacity. And permanent wilting point of most of the soil can be best approximated at a pressure of -15 bar. And available water is nothing but the difference between field capacity and permanent wilting point. And the term available water is slightly misleading. All the water which you see here is not available to the plants easily. There is a critical moisture content below which the plants they have difficulty in extracting moisture from the soil, and their growth and evapotranspirative process they start affecting. Okay, the next is drainable pore space. This is basically the pore space which drains or fills with the rise or fall of water table. And you see the formula for drainable pore space also, and this also depends on the property of the soil. If you have coarse sand, it has got 25 to 35% drainable pore space, whereas dense clay, it has only 1 to 2% drainable pore space. Okay, lower plastic limit is basically property of the soil, which tells you that the smearing of the soil or puddling or compaction when the moisture content of the soil is little lower than field capacity. Here in the graph you see you have saturated soil condition, and when the water is removed from the soil through gravity 2 to 3 days after irrigation or rainfall, the soil reaches the field capacity, and then below field capacity there is a certain moisture level at which the soil's moisture content is high, that soil can smear or puddle or compact. So that is basically the lower plastic limit. Okay, infiltration is basically the entry of water into the soil, and this is also dependent on the texture of the soil. Coarse texture soil, they have very high infiltration rate, 15 to 20 millimeter per hour. Medium texture soil have infiltration rate ranging from 5 to 10 millimeter per hour, and fine texture soil they have infiltration rate of 1 to 5 millimeter per hour. Another property is percolation, which is basically downward movement of excess water in the soil profile to underlying layers. In the process, upper layer drains to field capacity. Okay, now we will discuss about different type of drainage systems which can be used at the farm level. Uh, we have subsurface drainage system, surface drainage system, main system, and the outlet. Subsurface drainage system are used in soil in which the excess water is able to infiltrate and percolate through the main root zone to the water table and then move as groundwater flow through subsurface subsoil to the drain. In case of surface drainage system, uh, basically they are used in areas where infiltration or percolation of excess water is prevented or impeded at the surface or at shallow depths in the root zone due to presence of a layer of poor permeability. Main system is the system receiving water from the field system and then it conveys it to the outlet. Outlet are basically the terminal point of the whole system at which it discharges into the main into major element of natural open water system of region. Okay, there is another system of drainage known as biodrainage, and in this method we use evapotranspiration transpirative capacity of plants to remove excess water. And this water removal mechanism is not only low cost, but it also, because it does not require installation of physical field facilities and it does not require any disposal system. And there's a benefit of this method also that it may actually yield some marketable products such as fodder, fiber, and food. And but the problem with biological drainage is that it's not successful when crops are facing severe waterlogging problem, because in that case their roots will be destroyed and they will not survive. But this biodrainage is most favorable in arid zones or areas where drainable surplus are generally quite small in relation to evapotranspiration rate. At low evapotranspiration rate, for example, 1 to 2 millimeter per day, and limited evapotranspiration surfaces are there. Okay, now we will talk about surface and subsurface drainage method in a bit detail. Surface drainage methods can be classified into three groups. One is land forming for surface drainage system for flatlands, and surface drainage system for sloping lands. Land forming is basically reshaping of the land, and this is basically used in areas where uh, you don't have drainage problem or water logging problem to a greater degree. Just by reshaping the land, you can control or minimize the problem. Land forming includes land leveling, land grading, and land smoothing. Uh, land and in these operations, you basically remove high spots and fill depressions so that water can easily flow to the existing drains. And main objective of this land farming operation is to change the surface condition of the land to suit the requirement of surface irrigation, soil erosion control, moisture conservation, and surface drainage. And so land farming operation basically results in a regular plain surface, and which basically the ponding problem is minimized. Okay, there is a now we discuss surface drainage method for flatlands, and one of the such method is bedding method. In this method, furrows are produced by a plow which collect water from the field and discharge it into the main drain. This water is then conveyed to the field laterals and finally disposed of to the main drain. The next method is parallel field drain system. In this system, parallel but not necessarily equally spaced shallow field drains of greater capacity than dead furrows are constructed, which discharge water into the field laterals, as you can see in the figure. And these field laterals are placed perpendicular to the field drains, and they receive water from them for further disposal into main drain. And in this method, plowing is done parallel to the field drains, while other operations such as planting, cultivation, they are performed perpendicular to the field drains. Then there is another method known as a random field drain system. This system is used in areas where you have scattered depression and you do not need a complete drainage of the whole area. And what we do in this method, that we connect these depressions with one another by constructing a series of open drains, and then these drains carry water to a natural stream or a suitable outlet. And the cross section of these drains can be parabolic or V-shaped, as you can see in the figure also. Then there is another method known as parallel open ditch system. The difference between parallel field drain and parallel open ditch system is that parallel open ditches, they are of larger capacity, they are bigger in depth, and side slope is also steeper in case of parallel open ditch system. Here in this case, the depth of the drain varies from 0.6 to 1 meter, and the side slope, it is normally less than 4 to 1, and the spacing of the drains generally ranges from 60 to 200 meter. In this type of system, plowing and farm operations, they are performed parallel to the drains because they are deeper and steeper to be crossed by the farm machinery. Okay, now next we have subsurface drainage system. There are different layouts used in subsurface drainage also, and the first one which we will discuss is a random system. We have discussed this system in surface drainage also. This is also used in areas where you have some isolated wet spots. Complete drainage of the whole area is not required. In those situations, you are going to use this system. Here, the main drain is placed in the lowest depression, which receives water from different laterals located in different wet spots based on the topography of the land, as you can see in the figure. And since you are not draining the whole area, you are only addressing uh, those depressions or the wet spots. So this type of system is more economical compared to other systems. Then there is another layout known as grid iron or parallel system. And in this case, parallel lateral drains enter into the open drain at right angle from one side or both sides, as you can see in the figure. And this system is used under flat, regular topographic condition. And sometimes this grid iron system is also known as singular system. Uh, the disadvantage of this system is that it requires a large number of outlets into open drain, as there is no collector drain involved, and which creates some problem because these outlets, they are susceptible to damage and they may create hindrance to the mechanical ditch cleaning. Then we have one more layout in subsurface drainage system known as herringbone system. In this system, lateral drains, they run parallel to each other at angle varying from 60 to 90 degree from both sides of the collector. Here you have field laterals, then you have a collector drain, and then collector drain basically disposes water off to the main drain. And this system is also known as composite system, and this has been used in many areas of Pakistan where subsurface drainage system was installed. The main open drain and laterals run along the main slope, and the collector drain, they run across the main slope. And the advantage of this system is that large area can be drained with this system without much loss of land by open drains and less obstruction to the forming operation. But the disadvantage is high installation cost and clogging of the system, which could severely affect the productivity of the land. Okay, now we will discuss a little bit about the depth and spacing of the tile drains. Uh, Tile drains should be installed at a depth which should maintain suitable water level below the root zone for better plant growth. Basically, depth and spacing, they are interrelated, as greater depth allows for larger spacing and thus less number of drains. But the depth of the drains, it depends on the outlet condition, type of the soil, hydraulic conductivity, depth to impermeable layer of the soil, similarly kind of crop grown in the area, and the limitation of the equipment used for the installation of drains and their availability in the market, and repair and maintenance, as well as the cost of installation. All these factor influence the depth at which drains should be installed. Depth of although it varies with the soil, crop, and climatic condition, but it should not be less than 60 centimeter in any case, because in order to protect these drains from damage by farm machinery and heavy surface load. In Pakistan, tile drains were installed at a depth of 1.95 meter, 2.25 meter, and 2.4 meter. On average, you can say that at 2 meter depth to control waterlogging and salinity problem. The last point which we are going to discuss is the spacing of the tile drains. Spacing is basically mainly spacing of the drains depend on the depth of the drain, depth of the impermeable layer, hydraulic conductivity of the soil, irrigation, precipitation, and drainage coefficient. In irrigated areas of arid, semi-arid regions, drain spacing normally vary from 50 to 750 meter, and in humid regions where you have a lot of water, the drains they are closely spaced, and spacing range from 10 to 50 meter, but in good permeable soil it might be up to 90 meter. There are different formulas used for the uh, for calculating the spacing of tile drains. That is basically out beyond the scope of this course. Uh, there are two conditions. One is steady state condition, and other is non-steady state conditions. And scientists they have developed formulas for each of these conditions. But here we have provided you just a little basic information about the depth and spacing of the drains. And that's all about this topic on on-farm drainage.